All right. I would, and if I had Ben's last name in front of me, I would, I would introduce you properly.
It is Tippett, yeah.
Okay. Oh wow.
Okay.
Yes, aren't I helpful? But thanks for being here. And we wanted to discuss today the recent announcement of the not the discovery, but of the observation of gravitational waves, which was announced earlier this week, and I guess based on observations made in September, right?
From
Ben, is
two
that
LIGO, from two LIGOs.
Yes, that's right. That's right. Should I talk? I'm a
Yeah,
by all means?
that's why you're here.
All right, I'm so excited. Hello, everybody. Okay, so LIGO, it's this heroic effort. I am totally flabbergasted and amazed by the LIGO collaboration. Thousands of people have been working on this for decades, doing this heroic work. So let's briefly overview from 10,000 feet what happened. When really heavy things accelerate, they generate gravitational waves, according to Einstein's theory of relativity. And that's wonderful. It's wonderful. We predicted it. We knew that it was happening. Astronomically, we could observe the effects of this gravitational wave emission. So we were pretty sure it was happening. But we never detected it before. So what happened was, over the last 25 years-ish, some people there's a collaboration of universities in the United States and internationally who've been developing the theoretical tools and the actual interferometer that we use to observe these gravitational waves. It was a heroic feat, both theoretically and just experimentally. They did something totally amazing. And so what happened was they turned the machine on in September, and it started listening to the gravitational waves being emitted by the universe. And let's see the date. September 14th, they heard something amazing. Two 30 solar mass black holes collided. 1.3 billion light years away, two black holes collided. And we used our LIGO interferometer to detect the signal. And so the recent press conference, the reason all the physicists in the world are going bananas is because the LIGO people succeeded. It's absolutely fantastic. I want to talk to you about what they heard. That's fantastic. I want to talk to you about the fantastic machine they built. And I also want to talk about the heroic efforts that went in to building this machine and developing the theoretical tools to understand what they were going to listen to.
So now, Ben, we actually heard the gravitational waves. We didn't see the gravitational waves. Did we feel them or we heard them?
Yeah. So hearing, it's an analogy that's apt. Okay. And the reason it's apt is that the gravitational waves that were emitted are around within human hearing range, okay? But we're still talking about a signal that's being detected on a machine, just like how your digital camera detects light, and it detects essentially an electronic signal where a light comes in and wiggles the thing. Essentially, gravitational waves came in, wiggled the interferometer, and we recorded that and deduced that it was gravitational waves causing this. And we can talk about how we knew that it was gravitational waves and not somebody jumping up and down outside. But the deal is that when we say that we've heard it, it is an apt analogy because it's not really something that, for one thing, it's in the auditory range. So the signal that's coming in is about the same frequency as sound waves. And the second reason is it's not, the LIGO interferometers act as kind of a telescope, but it's not a telescope that we can point in any particular direction. It's kind of a telescope that sits and the signals come in, it detects the signals, and we deduce which direction the signals came from, and we deduce information about it based on having it come in, instead of us pointing a telescope in a certain direction and seeing what's out there. And so in two different ways, it's really analogous to sound waves. So people hear us calling it sound waves a lot. It's not sound coming from space. It is still just an apt analogy.
So SETI's not interested in this at all, then, is what you're saying.
I don't know how interested SETI should be in this. Maybe maybe really advanced civilizations can manipulate gravitational fields, and if they can, they'll generate gravitational waves, and we might be able to detect them. But this is a very expensive piece of equipment. I don't think SETI's SETI doesn't have the budget to build one of these.
This equipment detected a stellar event, an interstellar event that took place 1.6 billion years ago, which we're detecting now, and we detected it after a very recent upgrade to this equipment, which increased its sensitivity significantly, right?
Yeah. Oh, totally amazing.
What's fascinating to me about this is the speed with which it was detected after that upgrade. What does that say about the frequency of these events on an interstellar basis? I mean, it seems remarkable that we detected one so quickly after we got equipment that was suitable to the task.
Let's compare it to something. Winning the lottery, okay? So winning the lottery is a really, really rare event, and it's rare that somebody in your hometown, of a couple thousand people, wins the lottery. It's less rare that somebody in your home state or province wins the lottery. It's even less rare that somebody in your country wins the lottery, right? So in essence, when we scale up the population that things can happen in, they will happen more frequently. Sure. And so the deal is absolutely fantastic. I've got some notes here. I'm going to consult them just so I can get the numbers right. Between 2000 and 2002, 2010, it's called Initial LIGO. The LIGO collaboration built their first interferometer. That's those big L-shaped detectors. That's what's on the screen right now. We'll talk about that in a second. They built their first two, actually. There's one in Livingston, Louisiana, and the other in Richland, Washington. And they set up all their equipment, and they knew that it wasn't really sensitive enough to detect gravitational waves unless they were coming from quite close by, okay? But they kept upgrading and upgrading the equipment. So I would go to a physics conference. I work in a similar field, and the LIGO people would come, and we'd all be really happy to see them, and we'd say, have you detected any gravitational waves? And they say, not yet, but we're still upgrading the equipment. And so, near the end of that 2002, 2010 period, they had it developed. They had the technology. All of this stuff had been, tuned up. So they could hear potentially gravitational waves being emitted by something, but the distance out that we could hear was only the local group of galaxies. So if two black holes merged in our galaxy, we could have heard it. If two black holes merged in the Andromeda galaxy, we could have heard it. But farther out than that, the signal would become too attenuated. It would be too weak for us to detect. So what they did, 2010, they disassembled the whole thing, rebuilt it with fantastic new theoretically developed equipment. So they revolutionized the equipment. They put it in place, dramatically increasing the sensitivity. Now the sensitivity is so good on LIGO that we can hear two black holes colliding from up to 6 billion light years away.
Wow.
We've dramatically increased. Like local superclusters of galaxies, we've dramatically increased the volume of space that we're listening to, right? And so yeah. Okay, so the first number, let's see, millions of light years away. So if two black holes collided millions of light years away, we could hear it. That's pretty far to walk, but it's not all that far. Astronomical distances. Now we can hear 6 billion light years away. so far away, like much far. The volume that we're listening to is dramatically increased. And so as a result, we can detect these things. They're going to happen more often within our listening range because we've so dramatically increased the volume and the number of galaxies that we're listening to. And so it's not that strange that when they fixed everything and plugged it back in and hooked everything up and fine-tuned it and calibrated everything and finally turned the machine on, it's not so surprising that they detected this thing.
So, Ben, here 100 years ago, when Einstein came up with the theory of gravitational waves, it was just that. It was a theory. Now, of course, technology has gotten us to the point where the LIGOs were able. Do you think that there are other events out there that are theoretical at this point, that technology may allow us to, who knows, in 10, 15, 20 years, be able to actually verify and discover?
Okay, well, that's an interesting question. So the LIGO interferometer, it's essentially a telescope. It's a telescope that listens to gravitational waves. And this opens up a variety of interesting possibilities because we don't know exactly what we're going to hear. Now, it just so happened that the first thing they detected and had the press conference and published the paper on was something they were 100% certain they understood. Two colliding black holes. They knew it. It fit their models perfectly. Everything was fantastic. We don't know what else we'll hear. As we get better, as more interferometers come online, because there's only 2 right now functioning. Another one in Europe is being finely tuned, and it'll come online soon. There's another proposed LIGO site in India. The more of these we put online, the more accurate the data that we'll be able to interpret will become. And the more we'll be able to say, well, that's strange. What made that sound, right? So there's a little bit of that going on. In addition to that, Einstein's theory is fantastic, but it's not the only theory that's kind of like it. And so the future of gravitational wave astronomy might be that we can tune Einstein's theory or maybe replace it with something a little bit more accurate that theoretically exists today, but we're not sure if it's right, just because we can't usually measure what happens right up close to a black hole. So it's hard to say, because Einstein's theory of relativity was preceded by a bunch of by a bunch of astronomical measurements that we understood really well. We were sure of the data, but interpreting it was a little bit up in the air. We weren't sure. It didn't make sense in Newtonian gravity why things would be doing. Mercury was doing a weird thing as it circled the sun, right? Einstein's theory came along, displaced Newton's theory. So we're not sure if these the LIGO interferometer system, our way of listening to gravitational waves, we might see, or hear rather, things in the universe that allow us to have a better sense of which gravitational theory is more correct than Einstein's. Does it? Oh. All right. So
I think that's John trying to come back
John
in.
should be able to bring himself in now separately from the display.
I had one other question too. The 2 black holes. You said that they were the equivalent of they're 30 times the mass of our sun.
Yeah.
So together, this is 60 times the mass of our sun, but yet the black holes are only slightly larger, around the size of Washington, D.C.
Yes, it's because a black hole doesn't have any matter in it, or it's not made of matter. So what happens is you gotta go. The story goes back to how a black hole forms, at least as far as we understand it. The deal is that there's pressure, in essence. Pressure, interatomic, intermolecular forces are the reason that we can not fall into the center of the planet, right? There's a floor under me pushing me up. What keeps clouds in the air? Buoyancy and the temperature of the air around them. So there's a variety of things at play that keep things from falling down into the center of the Earth. But gravity wants to pull everything down into the center. So what happens in a star is when it gets really old, it kind of runs out of fuel. Stars work by essentially fusing two elements together. Doing so releases energy that generates heat. That heat is what puffs up the star and keeps it all from. It's essentially a big cloud of gas that wants to collapse down into a center, but all the heat generated in the middle keeps it from collapsing down. So what happens is if it's too heavy and if it's too, if it runs out of fuel, that heat no longer gets generated, and slowly the center starts collapsing. And then what happens is you end up with all sorts of weird catastrophic things. You get a supernova in essence. The core collapses, generates a wave of neutrinos. The whole thing blows off, and what's left behind is essentially a core of weird matter. And that weird matter can do one of a variety of things. If it's not really, really heavy, it can just kind of sit around like a big ball of metal. If it's heavier, it might collapse down into, say, a neutron star, which is just made of neutrons. It's a big ball of neutrons held together by gravity. And if it's even heavier than that, what'll happen is there won't be any nuclear forces strong enough to resist the push of gravity that's trying to compact it all down to a point. So what happens is it gets all crushed down to a point. Now, what's a black hole? Black hole is the gravitational field of that matter that's left behind. Because what'll happen in Einstein's theory of general relativity is that there's a radius around every mass. There's a radius associated with every mass, where if something's smaller than that radius, light won't be able to escape from the gravitational field. Okay? So essentially, all a black hole is it's the gravity, it's the space-time curvature that's left behind after the matter's collapsed down to nothing. So when we say these two black holes are colliding, really, we're saying these shadows, these remnants of gravitation, all that's left is gravity. All that's left is space-time curvature, whatever that is. And those two balls of space-time curvature are merging to make one big ball of space-time curvature.
That's crazy.
Yes. So when people say that a black hole's size is the size of Washington, D.C., they're not saying that the matter that there's a ball of matter that's the size of Washington, D.C. They're saying that radius past which light can't escape, that radius, if you fall into a black hole, you're crossing that radius. It's called the event horizon, or the just the horizon of the black hole. So what we're saying is
will there
those
be a
two
test
horizons
on this in the morning,
merge.
Ben?
Yes, and lots of math. So
Oh, brother. So Ben, my when I saw this graph here and I saw it live, they took the Hanford data separate, then the Livingston data, and then they reminded me of the movie Contact, where she called the other observatories. They moved the radio telescopes to a certain frequency, and they all saw the carrier frequency, right? But what is the vertical abscissa here? So it's over time. They call it strain, and it's 10 to the minus 21. What is that movement?
I'm not actually sure what this refers to specifically. 10 to the 21. It might be the distance between the differences in distances between the lengths. So it might be changes in the lengths of the interferometers.
The way it was presented, they were using a surface and bending the surface to demonstrate I think they were trying to represent the bending of space in some way, but I assume that, as you say, well, you're the expert. I gather it was, as you say, the measure of the distance between the mirrors are changing the distance between the mirrors.
To interpret what this graph says, could you load up that interferometer graph, please?
Yeah. Stand by, please.
By the way, if we were playing the interferometer drinking game, he has said that the word interferometer like 15 times now.
Canada's very cold, and it's important to stay very warm with alcohol, I think. What's in the center of gravity?
A 1, 2, 3. It's a Tootsie Roll.
Stand by.
That's the best thing I've ever heard in my life. Okay, so This is a schematic of an interferometer. LIGO is a type of interferometer. Before we go any further, I want to talk to you about what a gravitational wave does when it passes through something. Okay? Space-time is all about distances. The idea in Einstein's theory of gravity is that distance scales are dynamic things. I like to describe it in terms of like, okay, if I take two things and I hold them steady, the distance between them isn't changing, right?
Right.
Einstein's theory says that that's not always the case. The distance between them is a dynamic quantity, depending on, maybe a black hole flies between them, I don't know, whatever the case. That distance might change even though the objects aren't moving. Okay? So
where the introduction of a black hole within a certain distance of the interferometer would cause space-time to curve, and the distance would then...
if a black hole passed close enough to the interferometer, we'd be in trouble with that. But overall, this idea...
But yeah.
Overall, this idea is that distances can change. Okay, so the nice thing about video, I'm used to working in audio, right? So you don't get to do this. So what would happen if a gravitational wave passed through my chest?
It would rip you apart.
All right. So if I'm standing like this, the distance scale horizontally would compress.
Right.
Let's see.
Right.
The distance horizontally would compress, and my vertical height distance would stretch. So I'd go like
stretch arms.
Or rather,
exactly.
my arms would stay fully elongated, but my hands would get slightly closer to my body. And then, as it passed through, the opposite would happen. My height would compress, and my horizontal distance would elongate.
Right.
Why is that important? It's important because this is a basic feature of gravitational waves, and it's what the LIGO detectors were meant to detect.
Right.
So that's why they're shaped the way they are. Now, before we go on, let's talk about how strong this effect is, because gravitational waves, I mean, you saw in the video during the press conference, the whole world went, whoa, wobbled, right? That doesn't happen. We would know if that happened because we would like fall off our bicycles. Instead, it's a very, very, very subtle feature. Okay. So LIGO has these two arms. They're L-shaped. Each one is 4 kilometers in length.
Yep.
And what happens is we're continually measuring the lengths of those arms and comparing them. So if one arm shrinks and then the other arm gets longer and then it shrinks the other way, it means a gravitational wave has passed through it.
Right.
Does that make sense?
Yeah.
Now, it's a really subtle effect. Where's that? 1/1000th the diameter of a proton. That's how much it's shrinking and stretching, right? Like
that's crazy.
Nothing. It's so small. The distance between here, the one they said in the press conference, the distance between our star and the closest next star would shrink and change by the width of a human hair.
Right.
This is an impossible thing to measure. So here's what the tool is. Here's how we need to be able to detect essentially not how the lengths of each arm is changing. The clever thing they figured out is the only thing we need to detect is whether this arm is different in length than this arm.
Right. They show that because in that graphic. They show that in that graphic with the moving mirror versus the stationary. Yeah.
That's right.
So you're measuring the interference in the light beam.
That's right.
That's
exactly
correct.
The case. So the idea is we've tuned these lengths. We shine a laser down. Now the laser, this is a little bit disingenuous. The laser bounces back and forth between the center mirror and the upper mirror. They bounce up and down the chamber 15 times, I think. 75 times, I'm sorry, before they recombine.
Oh,
right?
wow. So why so many times? Just to...
Well, because this way... No. It's because this way, instead of a 4 kilometer arm on our L's, each of these 4 kilometers,
by 75.
4 times 75 times in their length, right? So effectively, they're hundreds of kilometers long.
Gotcha.
But even then, it's still going to be a really, really tiny effect. Yeah. So the idea behind an interferometer is the light goes down, bounces back. Light goes down, bounces back. It's like okay. So imagine each of these photons. It's a runner. It's a runner that we knew exactly how fast each it is. Right. So you take a runner, Ben Johnson, Canada's famous. No, Donovan Bailey, Canada's famously not disgraced runner.
No, yeah, he was disgraced. Yes, okay.
So Donovan Bailey was never disgraced. He won gold. We're very proud of him. So Donovan Bailey runs really fast, 10 kilometers a second, super reliably. So what we do is we take 2 Donovan Baileys and we start them out at the splitter and we make them run down the length of the tube and come back. And because they're so reliable, because the lengths of the tubes are exactly the same, when they get back home, they'll reach the center where they started at exactly the same time.
And cancel each other out.
So what is the tolerance that the 2 tubes need to be to? How close?
Bananas. I don't know that number.
Like 1 gazillionth of a meter or something, right?
Yeah.
Well, you know what? You talked about runners. JS has a specific question about runners. JS.
What was my question?
Superman versus Flash.
Oh, that's right. Speaking of which, so if Superman and Flash were in a race, who would win?
I think the Flash.
Oh.
Yeah.
Okay. There you go.
The sun sucks as well.
The interferometer, this is not, you can't just go to Radio Shack and get parts and make one of these at home, can you?
Well, you can make an interferometer, and people use interferometers in a variety of scientific tools. You can use them to measure. What's that?
I'll tell you something very similar. I worked for a company called Microtest in college in 1984, and we built the time domain reflectometer, which it works almost the same way, although we don't look for the differences and don't cancel out the beams. But we send a square wave down a wire, and we wait for the reflection to come back, and then we see if it's inverted or not, and then we measure it to see how far away the distances of the cables. It's pretty close to the same kind of phenomena, right?
That's right. The neat thing about an interferometer, it's actually a very old tool. It's been used for over 100 years, I know. It was one of the tools that they used to first bring in Einstein's theory of relativity. Special relativity was inspired by a measurement made with an interferometer. And you can use them for a variety of things. They're really, really good at telling whether those distances along the arms are changing. And that's useful for a variety of industrial applications, right? Maybe you're like, hey, I don't think that this camera I'm building is shaking to pieces, but let's measure how much the things are flexing. And you can use interferometry to do that. So it's a fantastic tool, but this is, world-changing in its accuracy.
So they got, and now because of this, they're going to get a ton of more funding.
Yeah, that's what's great about it, right?
Yeah.
Oh, it's so great. This was actually the National Science Foundation, I think, announced that this was the largest grant that they'd ever made, at least at the time. The funding on this project was absolutely immense. Well, it was an immense leap of faith.
It's amazing to me that this thing has sustained over the past 25 years through significant recessions here in the U.S. and worldwide, and they continued on believing that they were going to have an event like they had in September. It's amazing.
Well, yeah. I agree wholeheartedly. There were some interferometers. They were planning a space-based interferometer,
right,
that would measure. So it would be much, much larger than the LIGO facility. I'm afraid I forget how many thousands of kilometers.
Wow.
It would be a triangle-shaped interferometer, absolutely immense, and it had its funding cut in one of these recessions. So but LIGO made it through, and it did great work.
Oh, funding cut.
So it's amazing that this is unlike EMF, where we. Galileo came up with the telescope using visual spectrum and then radio and then X-ray. And this is another instrument that we can use to monitor the world around us. It makes sense to me that we would have these kinds of things to know what's going on in the universe around us.
Well, people don't really... So, before I go on, immense dividends. The technology required that had to be developed to make this thing, the amount of computational resources that had to be harnessed and well understood how to harness this immense machine, absolutely breathtaking. All that technology is going to pay back into the economy. It's like the space program.
Well, that's
fantastic.
That was that was JS's questions. He's like, how is this going to make me a better toaster oven?
Yeah,
exactly.
Well, who knows, but it will. Something about this, someone will say, hey, we can take this little part that we use to keep the mirrors from jiggling, and they'll plug it into your camera, and suddenly your pictures won't shake anymore.
I've been working on an interferometer oven. It cooks. But what you do is you separate the light, take the light beam, you separate it into separate lights, and then you come back in and you put your lean cuisine in there, and it does a really good job. The only problem is your kitchen needs to be 1.2 kilometers big.
Yeah, that's right. Yeah, but we don't know what gravity is. So how can you have the anti version of gravity? Oh, brother.
That is a very good pun. I get it now. It took me a second.
Oh, brother.
I don't know. So, and then there's that theory of Einstein's about when you drop the buttered bread on the floor, why it always lands buttered side down.
So you put it on the back of a cat, and you have anti-gravity.
There you go. Exactly.
So Ben, are you a PC gamer at all?
I am not a PC gamer. Yeah. I don't have the money to buy a fancy rig, and I don't have the time or the patience to develop the skills.
You're a poor college professor.
Yeah. I'm ashamed.
I mean, there isn't big bucks in the astrophysics biz. Is that what you're saying?
Well, I don't know. Maybe for Stephen Hawking there is.
Oh, Stephen Hawking does okay, yeah.
Well, Ben made the point that the technology from the interferometer will make its way into the economy and eventually be there will be consumer products that are derived from these technologies.
Yeah. But funding science. Yeah.
I was going to say, who really thought that?
Wait a minute, though. I just thought of it. What if self-driving cars, they're using LiDAR, and what if gravitational waves come through and fuck up all their LiDAR, dude? Big accident.
Well, you might miss your parking space by 1/1000th of a proton, but I'm
Damn
sure
it,
that you can walk the distance.
Don't blow my doomsaying predictions.
More to the point, though, you were saying that it was well understood what waveform might be presented by binary black holes.
Yeah.
Now the thing is, there are, like you said, many other things that might be detected with many different other waveforms, and where you look at, for example, sonar, the only reason that you're able to identify what you're pinging against with sonar, what you're getting, and the waveforms you're getting back indicate something meaningful, is because you know exactly what you're tested against. You know what enemy submarine is in proximity, because you know what the waveform is you're going to get back.
Exactly.
The point here is how do you go about evaluating what other phenomena you're going to be observing without actually observing them in some other manner?
That's a great question. There's two parts to it that I want to talk about. I'll answer your specific question, which is how can you hear something you're not expecting if you don't know what it's going to sound like?
Right.
I'll answer that in a second, but before then, this is exactly This is exactly like sonar. Imagine you're doing sonar for the first time, but you have no idea what anything sounds like. And you know that you're going to launch your submarine in 20 years or whatever, and you just have to figure it out. So what you do is you take thousands and thousands of graduate students, and then you make them essentially in the laboratory, in their computers, do simulations to see, okay, so if we bounce sound wave off this, what's it going to sound like? What's that sonar going to come back? We bounce it off a whale, what's it going to sound like? 250,000 templates. 250,000 different simulations have been made that are fit to the data as it comes in.
Wow.
So one of the two ways that LIGO detects gravitational waves, so essentially the deal here is we've talked about we're measuring these distances, wiggling, the distances between the mirrors is wiggling, and that's what we're looking for.
Right.
One of the ways they can wiggle is if any vibration happens anywhere near it, right? So somebody jumps up and down, that will cause the things to wiggle. Just a little bit. Everything's super isolated.
Angel's wiggling right now.
As isolated from the external environment as it can be. But there's still going to be some, a little bit of noise. In fact, you looked at that graph we showed earlier. There's noise. You listen to the LIGO sound that they play. Mostly it sounds like,
right.
It's just noise, acoustic noise.
Yeah.
So, acoustic thermal noise. So essentially, that's why they have two of them, because they essentially take all that data coming in and then they use the templates to see which possible thing, there's a little bit of noise and then you go, okay, well, this kind of looks like two black holes, but we don't know. They don't say, yes, we found two merging black holes, unless both the LIGO facilities, the one in Hanford, the one in Livingston, both of them, they don't say they've detected something unless both of them agree on which template it sounds most like.
Well,
so this is one of the two ways they analyze the data. There's two independent data analysis streams. So what they do is the data comes in essentially constantly, lots of noise and stuff. Yeah. And then they essentially take all that information and in real time plug it into templates to see if it looks like anything. And it's hard because noise looks like all sorts of things. So they can eliminate
ovens, Wi-Fi interference, whales.
Whales, right? People jumping up and down, trucks passing. Yeah. It's crazy. Yeah. But they can because they can compare it to the two facilities at the same time. A truck might be driving past this one, but it won't be driving past this one because they're on opposite sides of the continental United States.
Or earthquakes.
Yeah. Right. Yeah. So that's one of the various sources of error in this is earthquakes.
So, but you would like to be most efficient. Wouldn't you like to have like 12 of these things worldwide?
Oh yeah.
Yeah.
Yeah. That's right. Yeah. So that's why I said at the start of the show, we're really excited that they're going to build more. More are coming online in the near future, and more are being built in the longer term. India's just approved their LIGO facility. I believe. Yeah.
And so they'll all be tied together, so they'll be collaborative.
Yeah.
Yeah, that's right. Yeah. Just in the same way, so that they can.
I have the sounds right here from the waves. I believe you should hear them any second coming on here. This is
standing by.
Okay.
Yes, we've seen it.
No. What the people know is mostly about quantum mechanics.
Right.
So.
What is this?
Oh, that's a good question. I'm afraid I don't know the answer to that one. It's been a while since I watched What the Bleep We Know.
If they're measuring radio waves is totally different than what these instruments measure. They don't measure anything related.
Now, could the TARDIS traveling through time and space also distort things for the interferometer?
I believe so. Yes.
Okay.
Next question. Oh, right. I was in the middle of answering your other question. So there's two independent ways that LIGO analyzes. One of them is with this heroic number of templates, and the other is they just compare the signals and they see if there's anything weird that pops out. And so what they're looking for in that case
Mike,
is,
are you showing us your screen or something? Is that?
Yeah. What's?
Oh, the blab is up. Okay.
Oh, good.
Oh, is
Way
that
to go,
Mike?
Blab.
Why do we don't? Okay.
Yeah.
Yeah, blab is up.
Okay. Thanks.
Hooray.
Yeah, we're going to record it and edit it and throw it back up. I'll throw it back up on Blab and record it back into Blab so we have a good episode.
Yeah. So, actually, since we're looking at these waveforms here, they produced a model of these binary black holes based on this waveform, and because they had already understood the dynamics of binary black holes. What I don't fully understand here is, were these black holes at some point theoretically in a stable orbit and that orbit deteriorated, or were they never in a stable orbit and just
good
approaching each other throughout time? Because if they were in a stable orbit at one point, the next question is, what in the world could possibly have knocked a black hole out of a stable orbit?
Fantastic question. So, first question. Okay, so this is a computer simulation. This isn't footage of actual black holes. This is, I'll explain this in a second. It has to do with what we're going to talk about. So first off, the black holes they didn't just bump into each other in space. They were in orbit around one another.
Right.
In Einstein's theory of general relativity, there's no such thing as a stable orbit. All objects in orbit around each other generate gravitational waves. Those gravitational waves carry off energy, and then slowly they start to come together as the system loses energy, as they radiate away their potential energy.
Colin orbits around all hot chicks on Blab.
It's worked for me so far.
So essentially, these two objects were in orbit around each other. If we watched them a long time ago, we would describe their orbit as stable because it wouldn't change very much. Because the amount of energy that you lose in gravitational waves depends on how strong the acceleration is. It depends on essentially how close the masses are together. So before they're really close together, when they're really far apart, they might be in orbit around each other, but they're not losing energy very quickly. And so it would look to us over a long period of time like they're in a stable orbit. That said, once they get close enough together, the closer they get together, the faster they emit gravitational waves, the stronger the gravitational waves are that they emit. And so what will happen is you end up with this real runaway collision. Okay? So nothing weird. It wasn't an alien or a comet or anything totally bananas that knocked them out of a stable orbit. Stable orbits don't even exist. They're not a thing.
There you go. I told you it wasn't the Klingons, John.
Yeah. So eventually, the Earth will, other things will happen first, but it would be possible for the moon to eventually fall out of the sky and hit the Earth. Eventually, the Earth will fall into the sun. Other stuff will happen first. That's not how the world's going to end, but it could happen if,
is there a group or does somebody get to name? Does somebody get to name the singularities? Do they actually get names?
Oh, that's a good question. This black hole does have a name. This event that they detected has a name. It's BH and then a bunch of numbers. I'm afraid I don't have that name on me right now. You can follow it on Twitter though, and it's fun.
Like for $9.95, I couldn't call it Angel or something like that. Like if I wanted to do that.
Well, I don't. There are star naming programs where you can pay someone $20 and have your name entered into a star registry, but those registries are they're not very official. Astronomers will keep, even if you call it, you paid somebody to name that star Betty Star. astronomers will still call it, BH 1520309. Yeah, so
I think
I
Colin
shouldn't
would
do
call
that.
it-
I'm sorry.
I think Colin would call it D's nuts, right, Colin?
That seems appropriate here, doesn't it?
Well, eventually it turned into D's nut, right?
Yeah, which is really kind of a depressing thought when it comes down to it. Wouldn't you say, Sausage?
Yeah. So eventually,
There's a
then
horror-
everything is just going to like collapse upon itself, and the
That's a good-
universe will just
I
kind of.
don't think they know. That's conjecture, right?
There is conjecture about it. The current theory seems to tell us, or at least in the current framework, in the current theoretical framework, our astronomical observations seem to indicate that the universe is expanding at an accelerating rate.
Interesting.
Which means that everything in our galaxy will probably end up collapsing down into the central black hole at the middle of it eventually, long time.
Cool.
But other galaxies won't end up smushing up with our own. I guess, we're on a collision course with Andromeda, so that'll happen. But in the long time scales, far away galaxies will just recede away from us instead of collapsing down in on us.
Because
But eventually everything will be
Colin's
made of
actually
black
been
holes,
doing
yeah.
testing of this theory with pizzas, and he has a he did a
with
collapsing
great
pizza the other
success
night.
experimentally. It's been
Yeah.
Hey, Ben, I just wanted to thank you for your appearance
Yeah.
and your time that you've spent with us crazy
And your
guys.
patience. And Blab does not normally do this, my friend.
Well, that's
Sorry.
okay. I mean,
This is the first time this has happened to us. And we
I
recovered
understand.
quite nicely. And you obviously have a good sense of humor. I'd love to read the
Yeah.
Superman paper and see what that's all about.
Oh, you should. You should read my Superman paper and my paper about Cthulhu and my paper about the TARDIS and my paper
Yeah,
about Spider-Man. I was
I'm
just telling
working on
somebody
the
about that
TARDIS
today.
paper. That was my planned reading for this afternoon until I got sidetracked by these
And
bozos.
please feel free to call upon any of us if there's anything we can do for you. Or
I will.
Yeah.
yeah.
Absolutely. Love to have you.
I
John,
mean,
do you have any
sure.
of his links or any of that kind of stuff for Ben?
Well,
that you can
titanium,
pop
but
in here?
what's the real URL for titanium?
www.titaniumphysics.com.
It is, okay.
Yeah,
Because
you can just
when-
Google the Titanium Physicist podcast or look up the word titanium in iTunes. It shows up then too.
Right.
Yep. My podcast is released monthly, depending on when everybody can make it. I usually have 3 experts, including myself, 3 physicists talking to a layperson. So it's a fun show. We have a wonderful chat. We explain weird things that you never heard of. That said, it kind of depends on when everybody's schedules can make it. So
Right.
it doesn't get released regularly, but
So we have a lot of podcasters on Blab where they record simultaneous and they're on Blab. That way an audience can watch them record their podcast.
But they might be on
would-
5 or 6 different video and audio channels at one time.
Right. You'd bring additional audience to your show if you wanted to do that. We'd help you promote that. Yeah.
oh, that would be. I appreciate that, but part of the reason I can manage to get lay people on my show, people don't like not knowing anything in public. People hate.
Doesn't stop
being
me
on
at
a-
all. Doesn't stop me.
Yeah. So I managed to get them onto my show because I edit the show for content so that everybody involved sounds smarter than they are, especially me, but everybody, right? So
Yeah,
part of the deal.
You could sell a $49.95 course on to people on how to become astrophysicist life coaches.
For LinkedIn, yes, on LinkedIn.
LinkedIn.
Yeah. So I'm afraid my format doesn't quite work with these wonderful live shows. I really enjoy them. Very well done. But yeah, it's I kind of con people into it by saying, well, if it's too bad, we'll delete it. No one will hear it. And then they go, okay.
Yeah, so it's
Oh yeah, it's important.
So Leo Laporte used to have a science podcast, but they removed it. It was fantastic, and they had some of the best guys, around on the show. And I'm sorry that that was one of the ones they canceled because the audience is so small. People have no attention for real science.
Yeah, now we got to watch Mo Rocca. What the heck is up with that?
Crazy. Are you still recording? Yeah, I
We
think
might as well conclude.